Hey everyone, welcome back. Welcome to the beginning of Unit 10, Acids, Bases, and Salts. This is the first lesson in this series. We're going to cover the intro to acids and bases. So in the last set, we covered Unit 9, Kinetics and Equilibrium. Super exciting stuff. And this time, today, we're going to cover properties of acids and bases and the two different acid-base theories. Okay, so first, acids can be strong or weak electrolytes in aqueous solutions. And so remember, electrolytes, they're able to conduct electricity because they have free flowing ions. So acids and bases, when they're in water, when they're, in that aqueous solution, you have these different ions. And we get later on, you'll see this. But they can, conduct electricity either a little bit and be weak or a lot and be strong. Anyway, they are types of electrolytes. Acids, depending on which one it is, can react with metal to produce H2 gas. We'll get into that, later on in honestly a different unit, because that kind of goes hand in hand with the redox unit. Acids can change color in the acid-base indicators. So indicators, which we'll spend a whole video on, depending on the color, tells you what, the pH is. Acids tend to have a sour taste. And you kind of already know this. If you've ever had, eaten a lemon or had vinegar on something, you know it's very, very sour. And table K in your reference table has a list of all the acids that, you should be familiar with and be able to pull out of a pile of formulas. So table K is there. You don't need to memorize them. The more you work on it, you kind of will, just by accident, but table K is there. Bases, similar in some parts, they can also be strong or weak electrolytes. They also, too, cause color changes in acid-base indicators, but obviously a different color change would occur if it was a base. They tend to feel kind of slippery and taste bitter. So if you've ever eaten baking soda, even by accident, or you've put too much baking soda, those two are different, baking soda in something you're baking, you will taste that bitterness. If you've cleaned some kind of a sink and you've touched Ajax or something, that's ammonia, and it does have that kind of slippery feel to it. Just like acids, there is a part of the reference table that covers it and gives you a list of ones you should kind of be familiar with, and that is table L. Now, there are two theories we're going to briefly talk about today, and we're going to spend more time on the second one in the next video. But the first one is the Arrhenius theory. And this is kind of the more common acids that we see in more of the questions. And so this dude Arrhenius, he said acids and bases differ based on what ion is released in an aqueous solution. So he said acids release that H+, and bases release that OH-. Now, if you're looking at table K, so here's a screenshot of table K, you'll notice that most of the acids start off with that H. So when they're in an aqueous solution, so when they're in water, so if we just have, hydrochloric acid, for example, you have the H+ ion. And so acids are characterized by that H+ that is released. Now, when it's in that water, that extra H will attach itself to a water molecule and form H3O+, which is called hydronium. Now, if you think back, table E, our polyatomic ion unit, where a table does have, that up there. But for the sake of what you need to know, if you see H+ or H3O+, we're talking about acids. So they're not technically the same, but they're kind of synonymous with each other. Now, an Arrhenius base gives off these OH, or hydroxide ions. Again, the name and the formula from this comes right off of table E, those polyatomic ions. But, you'll see here, these bases are characterized by that OH at the end of the formula. And so, again, when it's in water, you have that OH ion kind of flowing around. Again, those free flowing ions in both the base and the acid, that's what allows it to be that electrolyte and conduct that electricity. So the next theory is the Bronsted-Lowry theory, and what they said is that acids and bases differ based on what they do with the H+. So they said acids donate H+, bases accept it. And so this four-letter word, bad, is used to kind of think about that. And what that stands for is bases accept, acids donate. And we're talking about that H+. Now, H+ is a proton. And so when we go into this in more detail, H+, proton is the same thing. Now, in a hydrogen atom, you have one proton and you have one electron. That's what makes hydrogen hydrogen. Now, if that electron is gone, remember if you lose electrons, you become positive or positive and you're a cation. And that's where that plus comes from. So it's just literally a proton. Now, acids will donate or give away a proton, or they have the capability to give away that proton, and bases have the capability of accepting that proton or that H+. So in this case, and we're going to spend more time talking about this in the next video, if we look at H and HCl, we know HCl is going to act as an acid because it's going to donate the H+ in order to become Cl-. And the only thing that's different between those two things is an H. Now in this case, water, and this one will pair together, and water in this case is going to act as a base because it's going to accept that H+ to become that. Now, again, these are called conjugate acid-base pairs. In the next video, we'll spend, the entire video going over that. But as long as you kind of think, just for right now, you're okay with bad, the bases accept, acids donate, and we're talking about H+. That's kind of all you need to know for right now. But on the last side, we mentioned that water was a base, but when we get later into pH scale, water is actually something called neutral. So in terms of the Bronsted-Lowry theory, water can act as both an acid and a base. So if we look at this water example, a water molecule, when it matches up with that, it accepted an H+, which makes it a base. But this one, we matched up with that, donated an H+, making it an acid. So water can play both roles. It depends on who it's hanging out with, it will do different things. And so the fancy sciencey word for that is amphoteric, meaning it can both be a proton donor, act as an acid, or be a proton acceptor and act as a base. So just to kind of wrap everything up with the one slide comparison, again, acids, again, we're always talking about H+. So Arrhenius says, gives off H+ in water. Bronsted-Lowry says, oh, hey, yeah, I agree, they definitely give off H+. Bases, on the other hand, Arrhenius said they give off OH-, and Bronsted-Lowry said they accept H+. So if we go back to, very quickly, table L, that common bases, NH3 is a base because it is able to accept another H, and it forms something else, which we'll get into later. So that is it for this video. Next time, we're going to talk in more detail about the Bronsted-Lowry theory and how it relates to conjugate acid-base pairs. Until then, have a wonderful day.